Okay, good afternoon. So today we learn about how we can use binary not just for unsigned numbers, but for negative numbers. So we want to make sure that we know the difference between signed and unsigned, which is really simple. Signed just means it can sometimes have a sign, a negative symbol in front of it. So you can have -3, as well as unsigned, which means it can only ever be positive. We want to make sure that we understand how 2's complement works. So there are two different ways of representing negative numbers. So far, though, we've only dealt with unsigned integers. Unsigned means it can only ever be positive, as in 0 or higher. Now, in maths, you determine whether something is positive or negative by writing a positive or a negative in it. But binary only understands zeros and ones. So we can't put plus or negative because they're not zeros or ones. So what you can do is just take the most significant bit. So yeah, the most significant bit is on the left. We can just say that that is the sign bit. But it's not a very good way of doing things. I don't like the slides for this, so I'm going to give up with the slides and just show you on paper. So let's say we have the number 8. You make sure you're writing the topic. So signed integers. And today's date is the 5th of October. My goodness. If we want a positive number, so positive number is exactly the same. So if this is sign and magnitude, we still have 1, 2, 4, 8, 16, 32, 64. But we can't have 128 anymore. It just becomes the sign. So positive 8 is going to be exactly the same in sign and magnitude as it was in unsigned. A 0 to say it's positive, and then a 1 for an 8. If you have the number -8, how would you represent that using sign and magnitude? So if we want it to be minus, all we do is just flip that sign bit. Otherwise, it's the same. So sign and magnitude is easy to do on paper. You look at the most significant bit. If it's a 1, it's negative. If it's a 0, it's positive. Otherwise, the other bits mean exactly the same. The only slight consideration is that it can only store smaller numbers. The maximum value you can have here is 127, because 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, all of those as ones, is only going to be 127. We do have a bit of a problem with sign and magnitude, because although it's easy for us to work out, if you add stuff, we have problems. So let's do something in English. Let's say 1 plus 1. Okay? The easiest we can do. They're both positive numbers. And if we were to add them together in binary, we'd just write them on top of each other in binary, wouldn't we? So we'd have 1 and then lots of zeros. It doesn't really matter how many. Plus, remember we did binary addition. I don't even know if I've got the right number. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, good. They're both positive. They've both got a 0 here. Add them together using column addition. 1 plus 1 is 2, which in binary is 0 carry 1. 0 plus 0 plus 1 is 1, and then we're just adding lots of zeros. So it is possible to add together positive numbers using sign and magnitude, because if you just use positive numbers, because it's exactly the same as unsigned. So let's be clear that what we're writing down here, this is sign, as in positive and negative, and, excuse the horrible handwriting here, magnitude. Magnitude means size. So this is the sign bit, positive or negative. This is the magnitude bit. How big is it? We have a problem when we start dealing with negative numbers. So let's do 10 plus -1. You know from maths that if you do add and subtract, that's the same as just doing 10 minus 1, isn't it? We expect the answer to be 9. If you add -1 to 10, it's the same as taking 1 away from 10. Agreed? No surprises. So let's work it out. Let's do it with sign and magnitude. 10. Well, let's think. 1, 2, 4, 8, 16, 32, 64, 128. No, just a sign. So 10 is 8 plus 2. That's a positive number. So the sign bit, you can't see what I'm writing, sorry. The sign bit is a 0. 8 plus 2. So that is our 10. We want to add that to minus 1. How do we do minus 1? Well, sign of magnitude is easy, but doesn't work very well. It's just 1 negative. Dead easy. But does it work when we do addition? Well, the answer is no, it doesn't work. 0, let's prove it. 0 plus 1 is 1. 0 plus 1 is 1. 0 add 0 is 0. 1 plus 0 is 1. 0, 0, 0. Add the sign bits and we get 1. So we've said if we take away 1 from 10, we end up with... So if we got this, that would actually be negative 8 plus 2 is 10, plus 1 is 11. Negative 11, which is wrong, horribly wrong. So although sign and magnitude is logical for us, it does not work in the same way for addition. So it is never ever used on modern processors. It's a terrible way of representing binary. We still have to learn it for your GCSE, but it's terrible. Why is it terrible? Because addition and subtraction doesn't work in a way that can be put onto silicon microprocessors in a way that works reliable. The whole point of a computer is to reliably do maths quickly. And that doesn't work with negative numbers. That doesn't bother us at the moment. We'll come to a better way. But for now, your job is to work through these. So remember, the first most significant bit is the sign. So this is negative. That's where that's come from. This is positive. So I'm going to put a positive in here. And what's going to be positive? Well, I've got 1 plus 2 plus 4 plus 8 plus 16. So in here, I'm going to write them in the order that they appear here. That's the 16. So I'm going to do 16 plus 8 plus 4 plus 2 plus 1. I'm showing my working as well as showing the actual result. So what actually is that? That's going to be 31, I think. Your job is to work through all of these. This is P5 in half term 1, please. So we said that there is a reason why sign and magnitude is rubbish, and it's because binary addition doesn't work. But there's another reason why it's rubbish, and this is it. If you look at this, that is 0. But if you look at the most significant bit, it's a 1. That tells us it's a negative 0. Which is weird, really, because 0 is neither positive nor negative mathematically. But from a computer's perspective, these two different binary representations both store the same value. That's negative 0 and that's positive 0. And there shouldn't be different representations of what is mathematically the same thing. So that's the second reason why sign and magnitude is stupid. But we still have to learn it anyway. So let's go through activity 2 and have some examples. So let's look at the example that we've got here and see if we can work out anything different. Well, the least significant bits, 7 of them, are exactly the same. So we've still got a 1, we've still got a 4, we've still got an 8, and we've still got a 64. But instead of this just saying that it's negative, all we've done is just say that that most significant bit is now worth minus 128. And that is the only change for 2's complement. And that one change is magical because it fixes both problems. Let's remind ourselves what those problems were. First problem was that it didn't work with maths, and it will work with maths. We'll prove it later. But 1, 2, 4, 8, 16, 32, 64, that's all the same. The only difference with 2's complement is the most significant bit is just negative. Why is that so important? It's so important because positive numbers can be the same. Let's go for plus 10. It's just going to be an 8 plus a 2 to get 10. And we have a 0 again. The 0 means that it's positive. If we want minus 128, all we need is that. And we don't add anything on to minus 128. There we go. Please. So let's do some maths, shall we? Let's do minus 128, add 10. And we'd expect it to be minus 118, wouldn't we? Let's do the maths. Add them all together. 0 plus 0 is 0. 1 plus 0 is 1. 0, 1, 0, 0, 0, 1. Now, we need to work out what this actually means. What we've got here is minus 128, add 8, add 2, which is minus 128, add 10, isn't it? So it is therefore minus 118. It works with addition, it works with subtraction, it's pretty magical. So if we want to be able to solve some of these, if they're positive, well, it doesn't really matter. We just keep it as positive because all of the ones with the most significant bit of 0 we don't need to worry about. Come on, word, don't be silly. So this is just going to be 32 again because we've got 1 plus 2 plus 4 plus 8 plus 16. If they're negative, so you've had a really good question. This is wrong and horribly wrong, isn't it? Because any number starting with a 1 is going to be negative. Let's check and see what it should be. It should be minus 128 plus 64, not add 16. No, sorry, not add 32, not add 16, but add 8 and 4 and 1. But that isn't plus 51. Let's check on a calculator and work out what it is instead. Plop that over there. Plop that over there. Let's go back to scientific. Help. Right, 64 plus 8 plus 4 plus 1. Take away 128. They've just got the sign wrong. This should be negative 51. Well spotted. So how do we do it? Well, we've just got minus 128 plus 8. No, sorry, plus 4 plus 2. What is that? That's 128 plus 4 is 124. Add 2 is minus 122. So I don't mind if you use a calculator to check this because I know some people get confused when you're adding to negative numbers. The trick though, if it's got a 0 at the beginning, it's a positive number, just like it was before. If it's got a 1 at the beginning, it's a negative number. And notice now, this is not minus 0. What is this value going to be? So yeah, this value is now minus 128 because the most significant bit is just now flipped to be minus. So let's look at a faster way of doing this. Hopefully you'll have got to this one down at the bottom. We know it's negative because the most significant bit is a 1, which means it's going to be negative. That most significant bit is worth 128. And then we add on to that minus 128, 64 and 32 and 16 and 8 and 4 and 2 and 1. Well, that seems like a bit of a pain. You can do that, but if you add all of those together, you're going to get 127. So 127, take away 128, which is the same thing as doing minus 128 plus 127. You're going to be left with minus 1 equals minus 1. There is a faster way that makes some of these questions a lot easier. So let's have a look at that. What we can do, and I'll use a different colour. If we start with the same numbers, 1, 1, 1, 1, 1, 1, 1, 1, 1, 2, 4, 8, 16, 32, 64, minus 128. If you know that the number is negative, and if you know that it's 2's complement, here's the trick. All you can do is invert the bits, which means all of the 1s become 0s, and all of the 0s become 1s. You can then add 1 and make sure that the answer is negative, and it'll work. This is 0. Add 1 to that. we get 1. Make sure it's negative. We've just got the result really quickly. Let's check and see if that cheeky way works for any of the others. We'll try it with this one, even though it'll be a pain in the backside. 1 and then lots of zeros. Let's see. 1 and then lots of zeros. We could, if we wanted, know that it's negative, so we'll invert the bits. What do I mean by that? I mean anything that was a 1 becomes a 0, everything that was a 0 becomes a 1. Work it out in denary, which is 127. Add 1 to become 128. So 127, add 1 is 128. Help. Make it negative, and it's what we had before. Although there's actually more effort for us, because this was just minus 128 in the first place. Let's try this one. So this is 1301010. Let's see. 10001010. Let's try. We know it's negative, so I'll invert the bits and add 1s. 0111, 0101. Work out what it is in denary. Add 1. Make sure it's negative. Okay, what is this? 1 plus 4 is 5. Let's write it out longhand. 64 plus 32 plus 16 plus 4 plus 1. Sometimes it's faster this way, sometimes it's slower this way. It's just a different way of working. So 64 plus 32 is 96. This is going to be 106. No, 112. Have I got that right? I don't know. 112 plus 5 is 117. Add 1 is 118. Have I got that right? No. I've messed up somewhere with my maths, haven't I? Yeah, sorry, I got the 8 instead of a 4. So the quick way to remember 2's complement, this is only necessary if it's negative. If it's positive, we don't need to invert the bits and add 1 because we just know that it's positive anyway. And then the next challenge is to see if you can work them out as 2's complement numbers. I'm going to give you a couple of minutes to have a go at that before we go through it together. All right, so let's look at the final activity. You could do this using the long method that we did before. Remember you had, let's use the camera to talk about this. Let's try and get that over there and this over here. In fact, it's probably easier, help, if this is maximized, but we can still see part of it. So you could, if you wanted, remember that you've got minus 128, 64, 32, 16, 8, 4, 2, and 1, and try and work out what combination of these gives you minus 8. We know we're going to need a minus 128 and work out what we need out of all of these, but it's a headache. Instead, what we do is we conveniently ignore the negative sign. And we just pretend that it's a normal, unsigned integer, 8. Because that's easy. We can just say it's 8. Like that, positive 8. We know it's not positive 8, but for now, that's our starting point. And then we use our trick. The trick is exactly the same. We invert the bits and we add 1. That's what it means by flipping and adding method in the question. So let's flip the bits. Anything that's a 0 becomes a 1. Anything that's a 1 becomes a 0. That's not the answer yet, because we need to add 1. How do we add 1? Well, we're adding 1 in binary. So let's see. 1 add 1 is 2. And then I've got 0, 1, 1, which again is 2. And then I've got 1 plus 1 is 2. 0 and 1 is 1. And then I've just got the bits here. So this, if we've done it right, should be minus 8. Let's check and see, shall we? Let's get a calculator up. So there's no chance of us accidentally getting the wrong thing. Put it on the other side of the screen and see. We want minus 128, add 64, add 32, add 16, add 8, that's it, is minus 8. It works. It seems like magic, but it did actually work. How did we do it? Well, let's choose one more as an example. Let's go for minus 13. Minus 13. We start with just pretending it's a normal 13. So how do we do normal 13? Well, let's see. All of these are too big until we get to 8, which we definitely need. How many more do we need from 8 to get to 13? We need 5. So that's our plus 13. Invert the bits. And add 1. This time adding 1 is nice and easy. 1 plus 0 is 1, and then it's just the same. And that should be our answer, and you can check it if you want. Minus 128, plus 64, plus 32, plus 16, plus 2 plus 1. If we've done it right, that will be minus 13. It's pretty magical. So that's as far as we're going to go today. In lesson, we've got another 10 minutes left, so do ask if you're struggling with this. It's not complicated when you've got your head around what you need to do, but until you've got your head around what you need to do, it does seem very complicated. And the trick to push through that is just to ask and work through it one-on-one. So when you're finished, save your Word document. It needs to be uploaded to half-term 1 data 1 binary. And then, as an extension, I'd like you to have a go at the data 1 revision quiz.